Morning, students. In this slide, we will like to focus on the concept of memory management in relation to operating system. In the previous sessions, we have already seen that how the CPU can be scheduled among a set of processes to increase the effective utilization of the particular computing system and to realize the increase in the operation or execution of the various programs. Also, we must keep several programs in the memory at a particular point of time. That means we also have to share the memory. Now, there are various types of memory management algorithms or procedures by which we can effectively organize the memory management in a particular computing system. So why are we implementing all those mechanisms, or why the memory management is very much essential? There are two basic points here. The first point is to ensure the protection of the different processes from each other. That means there should not be uh, any sort of interference among the operation of the various processes. And second point, to place the programs in the memory so that the memory is utilized to its fullest extent. Now, as because memory is also one type of resource, we should try to use that resource in the most efficient manner. Now, there are several approaches. Each approach has their own advantages and disadvantages. So basically, selection of a particular memory management scheme depends on several factors. Those factors can be hardware support or some sort of software design issues. So basically, the algorithms require hardware support, although the recent designs have integrated the hardware and the software to a much greater extent. So we will go through each of those mechanisms one by one. Now, basically, if we consider the memory consists of a large number of array of words or bytes actually, each with its own address. So basically a memory cell also has a particular address. Usually a program resides on a disk as a binary executable file. Now this program must be brought into the main memory and placed within a process for its execution. Now collection of the processes as the collection of the processes as on the disk waiting to be brought into the memory forms the input queue. You already know this thing. So basically, most of the systems allow a user allows a user process to reside in any part of the physical memory. Now, in most cases, a user program will go through several steps, some of which are optional, before being executed. So addresses may be represented in different ways during all those steps. Say for example, addresses in the source program are generally symbolic, such as count. Now a compiler will typically bind these symbolic addresses to some relocatable addresses, such as for example 14 bytes from the beginning of this module. Linkage editor is there. The linkage editor or the loader will in turn bind these relocatable addresses to some absolute addresses. Say for example, address 74014. Now each binding is some sort of mapping from one address space to another address space. So if we go to the next slide here, basically there are three different types of address binding mechanisms. Let me go to the slide here. So basically there are three different types of address binding mechanism. One is the compile time binding, second is the load time binding, and third is the execution time binding. Now what are those? So basically, if you know at the compile time where the particular process will reside in the memory, then absolute code can be generated. Say for example, if you know priorly that a particular user process resides starting at location R, then the generated compiler code will also start at that location and extend up from there. So if at some later time the starting location changes, only then it will be necessary to recompile this code only. So that is the concept of compile time binding. What is load time binding? If it is not known at compile time where the particular process will be residing in the memory, then the compiler, what it will do, it will generate some relocatable code. So in this case, the final binding is delayed until load time. So if the starting address changes at some later time, we need only to reload the user code to incorporate this changed value. And lastly, we have the execution time binding. Now this method permits moving a process from one memory segment to another memory segment during runtime. So in this case, the final binding is delayed until the runtime. There are some special hardware available for this particular scheme to work. Most of the general purpose operating systems, they generally use the execution time binding scheme. So these are the three address binding mechanisms. So basically, a particular process goes from one state to another to the address binding mechanisms. Now, what is the logical and the physical address space? Basically, the logical address space, a logical address is the address of an instruction or data as used by a program. So the set of address spaces used by the program is a logical address space. And what is the physical address? A physical address is the effective memory address of an instruction or data. That is, it is the address obtained after the binding of the logical address has been done. That means from the logical address, it changes to the actual physical address where from the data now what the instructions are being fetched during the execution of the particular instructions for a particular process. So basically it is some sort of binding mechanism. Now, if you go through this particular slide, then you can see that the logical address is being generated by the processing unit. Now, a particular relocation register is there, and it's part of the memory management unit MMU. The relocation register contains some base value. So combining the logical address with the base value, we are ultimately getting the physical address as shown in the particular diagram here. And ultimately, from that particular address, instructions are being fetched. So basically, all sort of instructions are being mapped from the logical address space to the physical address space through various mechanisms. So in the particular slide, you can see a particularly, you can say very basic scheme whereby some sort of relocation is being done. So basically the set of all the logical addresses generated by a particular program is a logical address space, and the set of all the physical addresses corresponding to these logical addresses is a physical address space. The runtime mapping from the logical or the virtual to the physical addresses is done by a particular hardware device, which you can see here. That is the memory management unit or the MMU. So in this way, the particular addresses are being changed. And lastly, what is the relocation register? So basically, relocation register is a special type of register in the CPU, and it is used for program relocation, means mapping of the logical addresses used by the particular program to the physical addresses of the system's main memory. So basically, relocation is a method of shifting a user program from one memory location to another memory location. Now, there are basically two types of relocation. One can be static or one can be dynamic. So static relocation, what is that? Static relocation takes place at the load time and remains fixed once the program is relocated, while dynamic relocation takes place at runtime. So the compile time and the load time address binding methods can generate identical logical and physical addresses. However, the execution time address binding or the runtime binding scheme results in different logical and physical addresses. So with that, we will conclude today's session here. In the upcoming sections, we will go into more depth into the concepts of memory management. So with that, we will be closing today's session here. Thank you.